In this video, I'm going to describe you the architecture of a sensor controller developed in the framework of the ELTAB project. This project concerns the development of a health monitoring system for elderly persons or patients. This work has been done for Analogies SA, and we're going to focus only on the parts of the ELTAB framework that you can see in this picture. The main device developed is the sensor controller placed in this prototype box here. The laptop is the gateway that gives instruction to the sensor controller on how to retrieve some measurements about the elderly person monitored, and the communication between the gateway and the sensor controller is performed through a router with a Wi-Fi access point. Now, in this closer view, we can see the various parts used in the sensor controller. Most of them are readily available boards. For example, you can see an Arduino Uno board, the blue PCB on the right. On the left we have a Raspberry Pi module and several boards stacked on it. For example, over the Raspberry Pi there is the Arduino bridge that gives a pinout similar to that given by an Arduino board. Then we have the eHealth kit by Cooking Hacks, which is the actual sensor controller where all the medical sensors can be connected onto. In this picture you can see three sensors connected. At this connector here we have connected a respiratory sensor. A temperature sensor is connected at this connection here, and an oxygen level at the blood can be measured through a third sensor placed at this connection here, at this connector here. Between the eHealth module and the Arduino bridge there is a Wi-Fi module that takes care of the communication between this sensor controller system and the gateway, which is the laptop shown you earlier in this previous picture. You can also see here that there is a breadboard where several relays have been placed here. As you can see later, the purpose of these relays is to control the sleep mode of the Raspberry Pi, because otherwise Raspberry Pi does not support an appropriate sleep mode, and the continuous current consumption would force the recharge of the batteries used if this module is used as a mobile system that, for example, can be carried by the patient himself. And moreover, there are two relays that control some connections between sensors that have a conflict if they are connected concurrently. And these sensors are the electrocardiogram and the electromyogram sensors. We're going to describe right now this functionality. So let me open a PowerPoint with some figures that describe the operation of this module, and this will help understand later the demo that I'm going to show you with the communication between the sensor controller and the gateway. So first of all, as I told you earlier, we have a gateway which is actually a laptop where an FTP server has been installed on it. and on the right we have the sensor controller, the box where the boards have been placed in that I showed you earlier, and a router with Wi-Fi access point that takes care of the communication between the sensor controller and the gateway and its FTP server. Now, the purpose of the gateway is to instruct the sensor controller on how often to sample the various medical sensors, and this is done by preparing a protocol TXT file that contains the instructions on how to do the sampling, and the results of this sampling, the values measured, are placed in a different file named data.txt. That is, let me throw out this picture. Okay. Now, the results of the measurement can be placed on different files called data.txt that are sent back to the FTP server at appropriate time intervals. The protocol.txt file may contain some time intervals where no action is required by the sensor controller, and if these intervals are shorter than 1 minute, for example, then the Raspberry Pi, which is actually the microcontroller that takes care of the sampling, simply does not do anything, and some of its modules may be deactivated to consume less power. But if we're talking about time intervals longer than 1 minute, then we have decided to turn off completely the Raspberry Pi because it does not support any hibernate state or sleep mode for low power consumption. And as I told earlier in my presentation, this would require an often recharge of the battery if the module was used as a mobile sensor controller. You will see in the following slide how this low power configuration can be performed using a second microcontroller board, which is an Arduino module. I have also to tell you that in the place of the sensor controller we had either to use an Arduino board or a Raspberry Pi module, and Raspberry Pi was chosen first of all because it offers a very larger memory for sample storage and sample processing. It offers a very friendly user interface that can help in debugging and developing all the necessary modules, software modules. And then we had also another issue with the Wi-Fi transceiver that could be placed easier if we used the Raspberry Pi module. So, although we used the Raspberry Pi module in the place of the sensor controller, we also used, as I showed you earlier, an additional Arduino microcontroller board to control the relays and implement the low power mode where the Raspberry Pi is completely turned off. You can see the same configuration here, but with some different paths. If in debug mode, we are going to show you later exactly in this debug mode the operation of the whole system in order to watch the several messages that are produced throughout the operation. And as you can see here, although in the previous slide the gateway would communicate with the router access point either in a wired or in a wireless module, but the sensor controller had to communicate with the router only in a wireless mode because the sensor controller is a mobile module. Then in debug mode we both support the wireless communication path as well as a wired communication path for the debugging of the whole system. And on the gateway, on the laptop that implements the gateway, we have a terminal, as you will see later, where the Raspbian OS environment is presented and the various messages produced throughout the operation are shown. Now, as I told you earlier, there is a breadboard with some relays placed there, and in this slide I show you the exact use of these relays. First of all, on the first dashed box on the top left of this slide, you can see the Arduino board. And at the bottom right of this slide, you can see the Raspberry Pi module. The main power supply of the system is a 6-volt power supply that can be provided either by a set of batteries or by a power supply module. We have used the embedded 5-volt regulator of the Arduino Uno board. And we take the 5-volt output of this regulator and use them in order to give a power supply to the Raspberry Pi module. But this power supply is given through a relay called S1 here, which is controlled through P1 plus and P1 minus pins that are generated from or controlled from Arduino Uno board. I will explain you later why this configuration with the 4 MOSFET transistors has been used. You can also see another pair of relays controlled through NIM channel MOSFETs here that can be used to select between the electrocardiogram or electromyogram sensor, and the control of the two relays is also done by another pair of pins from Arduino Uno board. The Arduino Uno board is also connected to the Raspberry Pi module through the USB port, but we use the 3 of the 4 pins of the USB port, the D plus D minus for data exchange and the ground for common ground, but we have disconnected the power supply mode. As I told you earlier, we require when long intervals where the Raspberry Pi module, which consumes most of the power, does not have to do anything, we try to power down this module. So this is the reason why the relay S1 has been used, because the relay S1 through P1 plus and P1 minus controls when the Raspberry Pi will be supplied or turned off. If we had used the USB connection with the power supply, although we would have turned off this line here, the plus 5 voltages here, the Raspberry Pi would receive power through the USB port, which is something we do not like. And that's the reason why we have disconnected the power supply from the USB module. Now, let's suppose that power supply is initially given to the system through the 6-volt power supply here. Arduino Uno is all the time powered, although there are several time intervals when it goes to sleep mode. Sleep mode is supported in Arduino Uno board, and some intervals, maximum of about 10 seconds, can be supported. But if we like to have sleep modes longer than 10 seconds, then we can use the EEPROM of the Arduino Uno board and store there a counter to count how many intervals of 10 seconds are needed in order to support longer sleep intervals than 10 seconds. So, When the power supply is initially given, both Arduino Uno and Raspberry Pi are powered on and start the operation of the sampling. First of all, as you can see later, Raspberry Pi communicates with the gateway, receives instructions, starts sample the various medical sensors, and then for some time it has to return back to the gateway the values. But the question is what is happening in this system here when some long time interval is needed. In order to support long time intervals longer than 1 minute, Raspberry Pi sends an appropriate instruction through the USB port to the Arduino Uno board, and Arduino simply turns off through relay S1 the Raspberry Pi and counts intervals of 10 seconds, as I said earlier, in order to construct the longer interval it has to preserve as turned off the Raspberry Pi module. Then when this interval, the sleep interval, ends, Arduino Uno instructs the relay S1 again and turns on again the power to the Raspberry Pi, which boots again and continues its operation from the point it stopped. Moreover, Raspberry Pi can also give Arduino Uno some instructions on whether the ECG or EMG sensors are connected in order to do some appropriate measurements there. A question is what kind of relays should be used in this configuration, because as you know, relays consume a lot of power. For example, with a 5 voltage supply, the relay can show a resistance of 100 ohm or at most 500 ohm. This means several milliamperes have to be synced through the relays. And so using appropriate relays for lower power consumption is a crucial issue. For the powering of the Raspberry Pi, we have used a relay S1 which requires short intervals of about 150 milliseconds of an appropriate polarity to either close or open the switch of the relay. And since we like to drive these inductance of the relay through, or control the inductance of the relay through pins of the Arduino board that cannot supply much current, we have used this configuration here, which seems like a CMOS inverter and another CMOS inverter on this side. Indeed, we, for example, either allow current to flow in the direction from left to right, or current to flow from the direction of right to the left, according to the polarity of P1 plus and P1 minus. But the path from the VCC to the ground is only active in either case for a very short interval. Then the relay stays at the last state posed by the polarity of these pins. In other words, the relay S1 is not always consuming current. It only consumes current at the time where the state of the switch has to change. We have also used different kind of relays for the control of the ECG and DMG sensors here, shown in very oftenly used configuration. But we can also say here that a configuration like the one used for the power could also have been adopted for the ECG and DMG sensors. Although we can also choose some relays where, for example, the normal state is either closed or open, and we can choose what kind of relay we like according to which state the relay stays on most of the time. As you can understand, we would choose a relay that consumes power only during the states that are short. I think enough said for the relays used in order to support low power mode of this system. Now, before showing you and describing this flowchart that describes the firmware of the system, it's useful to show you an example of a protocol txt file, and this is the one that is going to be used with the demo later. Now, what you can see here is a protocol txt file where the first line just defines whether we are in a run or a stop mode. In run mode, two parameters are defined at first. The first number is called quantum, Q, and the second is called interval, interv. Will be this name will be used in the following descriptions. If we had, for example, the first line of this file to start with a capital S letter and the number, then we would mean that we would like to have a sleep mode for 100,000 milliseconds, which is 100 seconds. This is more than a minute, which means that the Raspberry Pi would send to a deep sleep, as we will call it, meaning that the Raspberry Pi will be totally turned off, while we will mention as light sleep mode intervals not implemented by turning off the Raspberry Pi, but simply doing nothing or deactivating some minor modules on the Raspberry Pi system. So let's keep the line used at the beginning, which starts with a capital R, meaning run protocol, which means that sampling will be performed. And I repeat that the number 100, the value 100 is called parameter Q, and the value 70,000 will be called parameter interv. Then 9 kind of sensors follow, and a different number is listed below each sensor name. You can see here that for the sampling of the oxygen level in the blood, which is the first line, we have defined the number 50. Several sensors have corresponding a number 0. Airflow sensor has been assigned number 2. Body temperature sensor has been assigned with the number 10, and galvanic skin sensor has been assigned with the number 100. This means that the SpO2 sensor will be sampled every 50 by Q milliseconds. 50 by Q, which is 100, is actually 5,000 milliseconds, which is 5 seconds. So SpO2 will be sampled every 5 seconds. The ECG sensor will not be sampled at all, since it is given the number 0. Airflow will be sampled every 2 by 100, which is 200 milliseconds, or 0.2 seconds. Body temperature will be sampled every 1 second. Then we use galvanic skin sensor, which will not be used at all, and be assigned with a relatively large number, 100, which means that it would be sampled every 10,000 milliseconds, which is 10 seconds. This is actually a dummy read in order to define when we would like to end the first stage of sampling of all these sensors, and after this stage, which means after 10 seconds as I estimated earlier, the interval of 70,000 milliseconds or 70 seconds will be used as a sleep mode, as a deep sleep mode, and then afterwards the sensor controller will contact again the FTP server on the gateway and retrieve another protocol TXT file. Meanwhile, the gateway could have changed, modified this protocol file with some different instructions as will be shown earlier. So, at this point, we can return back to the last slide here, which describes actually what I showed you earlier concerning the protocol TXT file. So when Raspberry Pi starts, it initializes, of course, the Wi-Fi interface, the FTP communication, as well as its USB interface. Then protocol TXT is read from the FTP server, and according to whether the protocol TXT file defines run or sleep mode, two different paths can be followed. If sleep mode is defined, then a sleep interval milliseconds is followed, as you can see here, and then the protocol TXT file is read again. Otherwise, if a run instruction was given in the protocol TXT file, then we have a nested double loop, double iteration here, as you can see, where in the internal iteration a counter I is used, and when the modulo of this internal I counter with the numbers defined in the protocol TXT file for each sensor, which is called capital N, if the modulo of this value is 0, then this means that the specific sensor should be sampled at this point. Otherwise, no sensor is required to be sampled, and the counter is simply increased by 1. When a sensor is sampled, then the value retrieved from the sensor is appended to a data.txt file. Between each increment of the counter I, a Q milliseconds interval, sleep mode, is used. Then we check if the counter I has reached the value of the dummy NK, which in the previous example was a sensor, the ECG sensor, that will not be read at all. And if this value has not been reached yet, the internal iteration, the internal loop continues. Now, when the value of the dummy sensor read is reached, the internal loop has to end, so either we sample or not this dummy sensor, and then we sleep for another interval milliseconds time, which usually will be a long interval that will be implemented as deep sleep. And then the control starts all over again. Although the control should normally start at reading again the protocol TXT file from the FTP server, I put the arrow here showing that the whole operation starts all over again, because it's easier to implement when the system, the Raspberry Pi module, boots again and starts operating from the beginning. So, after these explanations, we can demonstrate the whole process. With this screen capture, we can both see what happens on the gateway and on the sensor controller. I have to tell you first of all that in order to communicate with the FTP server, the firewall has to be deactivated, or an exception to be simply added. This is the most appropriate way to do it, to add an exception in the firewall. And then we should start the FileZilla server installed on the gateway. I leave this this window here. Then we have to connect the gateway with the ELTAB access point, which is the one for the communication with the gate server. Now at this point I'm connecting wirelessly to the gateway. Okay, and now I can turn on the power of the module. Of course you cannot see this from this screen capture here. Immediately both modules have been turned on, and in a while I can use a PUT shown here to connect through the gateway and the Ethernet that connects the router to the sensor controller to the Raspberry Pi module. Static addresses have been used, not here but at the debug mode, but static addresses have been used in order to find at the same IP address the file, the FTP server and the sensor controller too. In the Raspberry Pi module there was a script defined that starts running immediately when Raspberry Pi boots. Okay, now I put the correct password. The working directory is this one here, and here you can see several files. For example, the messages are all the time stored in a file called ELTAB_log. You can see here that when I cut this file, the messages changed. At this point you can see that the IP addresses and the network connection is initialized. Then some things concerning the FTP server are initialized. This new configuration has to be saved, and a reboot on the Wi-Fi module is needed at Raspberry. We can also watch this progress here through a tight VNC server. For example, when I'm here, I can also cut the log file. Now we're at the point where the default ECG sensor is defined. You can see some messages concerning this one here, and now the protocol txt is used. You can see from file Zilla here that in a while a communication will take place between Raspberry and the FTP server in order to retrieve the protocol txt file. So if we still continue to watch the log, we can see several messages showing that the system is connected to the ELTAB router and the FTP server, and as you can see from the messages shown here, a communication has taken place to retrieve the protocol txt file from the FTP server. What can we also see here is that the script that runs on the boot of the system is placed in this position here, which is a file called local.rc.local, and this file can be found in /etc/init.d. Actually, the tight VNC view is not required. I can disconnect here, and I can simply watch the log file from from this window. Now the loop has the internal and external loop has taken place, and at this point the communication takes place from the FTP server with the gateway in order to transfer a first data file on the side of the FTP server. The communication is slow enough, as we're gonna see here, because actually the FTP is not performed by transferring full files from the sensor controller to the FTP server. Instead, the file transfer is performed by opening opening something like a terminal, let me say, and throwing inside this terminal strings which are the messages that we would like to transfer. And then at the end, the whole process ends using a timeout when the transmitter stops sending information. After a timeout, the FTP server closes the file and the communication seems complete. Now, when this file transfer ends, we will see that a shutdown message will appear here, showing that a long interval will be performed and the Raspberry Pi will be turned off by the Arduino board. So I think we're close enough to this point. Then when the system will be turned off for the implementation of the deep sleep mode, when the system wakes up again, I will leave the same protocol.txt file, and the same sampling scheme will also be repeated once. And this time I'm gonna wear the 3 sensors in order to view the exact measurements taken at the second round. Then at the third round I'm gonna change the protocol.txt file and replace it with one that simply lets the system sleep. And then we will turn off the whole system here. Okay, this is the point where the system is going down. Now the connection is lost from PuTTY. Although you cannot see here at this, you cannot see it at this point. I'm describing you that Raspberry Pi has not been completely turned off yet. It requires about 40 or 50 seconds to do a complete shutdown, and then the relay has to turn off the power. So at this point the shutdown has not been completed yet. Now the shutdown has been completed, and in a few seconds the relay will turn off. Okay, now the system is turned off. In a few seconds Arduino will turn on again the Raspberry Pi, and we will be able to connect again and watch the log messages in more detail. Okay, at this point Arduino has turned on the power to the Raspberry Pi, and the system starts booting. I'll try again to connect through PuTTY. In order to monitor the progress of the system operation. It's not ready yet, so the connection cannot be done, but I guess that if I try again, this time I will be able to connect. Okay. Alright, so I'm moving to the working directory and watch the log. So you can see here that the initialization has started. First of all, the network is initialized. Then some parameters of the FTP connection should also be initialized. At this point, the parameters have to be saved, and a reboot of the Wi-Fi module, which is an RN171, the type of the Wi-Fi module. Okay, reboot has been completed, and again some parameters are set. You can see that the phrase for the WLAN connection has to be defined. All these messages can be deactivated during normal operation, but they are on at this point in order to watch the whole process. Then we can see that the Raspberry Pi has been associated to the ELTAB access point. Then the default ECG sensor is selected by these messages here. And now the retrievement of the protocol txt file will take place. Okay, you can see on the right that the protocol txt has been just transferred. The protocol is analyzed. It will take some time. First of all, because the end of the protocol transfer has to be indicated by a timeout interval, and for this reason we have a significant delay at this point. Okay, this is the protocol txt file. I've already described it to you earlier, and now measurements have started to be taken. So I'm touching the temperature sensor and breathe on the respiratory. Okay, sampling has ended. As you can see at the FileZilla window, transfer has been performed at this point. Data transferred. Meanwhile, I'm also changing the protocol txt file to a sleep protocol. In order to lead the system to a sleep mode next time it will read the protocol txt file. For the present, the data txt is sent. It will also take some time, as we saw earlier. The values retrieved by the sensors can also be seen here. For example, you can see the values of the airflow sensor in this log. Sometimes earlier we show the body temperature value, which was about 35 degrees Celsius. We will see all the values retrieved later as they arrived at the FTP server. Okay, I think at this point the shutdown will also take place due to the deep sleep interval that has to be performed. Transfer of data has not been ended yet. Okay, system goes down in order to implement the new sleep interval. The system is shutting down. It has not been completely turned off yet. This window is not needed anymore. At the end of this demonstration, I will also show you exactly what happens at the boards during this interval. So at this point I can inform you that the relay turns off the power. That's the sound of the relay you just heard. In a few seconds Arduino will turn on again the Raspberry Pi module. Okay, system starts booting again. I will try to connect for a while to see just how the new protocol.txt file will be interpreted. Okay, plug in. And I move to the working directory. Initialization of the network and the FTP client takes place. FTP client is initialized now. The address of the FTP server is set at this point, at the bottom of this window. The username and password are also defined, as well as the port, of course, of the FTP communication. Timeout is set to 80 seconds in order to close a file. This information is changed in configuration, and a reboot of the Wi-Fi module is performed right now. At this point, the password for connecting to the Wi-Fi, for associating with the Wi-Fi module, is defined. this message shows that the sensor controller is already associated. As I told you many times, the ECG sensor is selected by default, and now the protocol.txt file will be retrieved again from the FTP server. As you will see from this window here, the FTP communication will take place in a few seconds. Okay, at this point protocol.txt has been transferred to the sensor controller, and the parsing of this protocol will take place. It will be shown shortly that when the first line shows that a sleep has to be performed, the system will immediately shut down. Parsing has not been completed yet. Okay, and now you see that immediately we will receive sleep mode has been recognized, and will immediately receive shutdown message. So system goes initially without any sampling to shut down and perform the sleep interval defined. What I would also like to show you was the values retrieved earlier here. You can see this file, it's better to open it with WordPad, and you can see the various values here. The airflow was most of the time 0 because I delayed to place it near my nose and start breathing in it. So you can see some values different than 0 at the late samplings. For example, here a deep breath was taken and 153 was retrieved, while the temperature was 33 degrees Celsius initially, and when I touched this sensor it was raised to more than 35 degrees Celsius. Now at this point the system has been turned off for implementing the sleep mode. And now the system will boot again. I will not repeat describing you the whole process. I will just proceed immediately to showing you what happens on the boards during the next sleep process. At this point the shutdown of the Raspberry Pi takes place. You can see some LEDs here that are going to be turned off gradually as shutdown proceeds. The LED blinking at the bottom here is the Wi-Fi module. Okay, so the shutdown is completed, as you can see from the LEDs that have been turned off. And now Arduino has completely turned off the Raspberry Pi. You can also see here a LED that will blink, which shows the intervals where Arduino wakes up and schedules. Okay, you can show that LED that was lit now, and shows the exact intervals where the Arduino wakes up and sleeps again, in order to schedule another 10-second sleep interval. This LED is on and off for 10 seconds, for about 10 seconds. Okay, now the sleep interval has finished and the LED gave power again to the Raspberry Pi, so you can see here that various LEDs are lighting again, showing that the Raspberry Pi boots again in order to start the whole procedure and retrieve again the protocol.txt file and do any sensor sampling scheme required. Thank you very much for your attention.